A very good evening to all the delegates and participants. We are still waiting for the participants to join. So we request you to stay connected. We'll start soon. Thank you. Thank you for your kind cooperation. We welcome Dr. Deepak Reddy sir for this session. Thank you for joining this session, sir.
Yeah, thank you very much.
Yes, sir. Sir, we are waiting for participants, sir. We'll start in a couple of minutes.
Okay.
Thank you. Thank you very much. We once again request the participants to stay connected. The program is going to start in 2 minutes. Thank you for your patience. Thank you.
Good evening, madam. Good evening, ma'am.
Good evening, madam. So it's time to start the session. This is Rajesh, Assistant Professor, Department of EEE, Vidya Jyoti Institute of Technology. Team EEE welcomes you all for the 1-week faculty development program, International Faculty Development Program on applications of power electronics in renewable energy sources and electric vehicles. So the next 5 days are going to be wonderful days for all of us. I welcome all the speakers and I welcome all the delegates and the participants to the program. And before starting this program, I request our principal, Dr. A. Padmaja ma'am, who always motivates us, inspires us, and pats our back to conduct such programs. Madam, I request you to address the participants and delegates of this program.
Good evening, everyone. First of all, I would like to congratulate the EEE department, Dr. Sujana and his team, for conducting this FDP, which is very essential and it is a very hot topic also. I hope all the participants from this FDP would learn immensely and gain knowledge immensely from this various experts. I heard from Dr. Sujna that various experts from other countries have joined to deliver lectures in this FDP. And I wish you good luck to all of you. And thank you very much once again. I just reached home actually, connected through mobile and yeah.
Thank you, madam. Thank you
Yeah.
very much.
Thank you for your motivational words, ma'am. Thank you.
What is
Now,
the first session today?
today it's on distributed control scheme for DC microgrids, madam.
Okay, okay.
By Dr. Deepak R. Pulugaram from IIT Kharagpur.
Okay, okay. Very good. Continue, Rajesh.
Yes, ma'am. Thank you, ma'am. Now, I request our professor and head of the department, Dr. A.S. Rujana, ma'am, who is the main reason for conducting this session. Ma'am, I request you to inaugurate the session by your inaugural speech.
Thank you, Rajesh. Respected principal, madam, colleagues of EEE department, and participants of this international FDP on applications of power electronics in renewable energy sources and electric vehicles, and the eminent personalities who have accepted our request to deliver sessions in this particular FDP. Very good evening to all, and I welcome all the participants for this particular FDP. So the main aim of designing and conducting this particular FDP is to enrich knowledge of faculty through interaction with eminent personalities drawn from industry as well as academia. Knowledge sharing will improve the teaching learning process to the students and benefit the society. Coming to the topic of the FDP, the need for distribution generation, employing renewable energy sources such as wind, solar, and fuel cells has gained significant importance because of the rapid increase in global energy consumption with a transition towards green energy. As we all know, power electronics plays a crucial role of conversion and control of electrical power. Power electronic based converters are widely used in renewable energy system. Power electronic interface has to regulate the voltage, frequency, and power to link energy sources to the grid. So eminent speakers will address on challenges and control schemes for this grid integration with renewables. And as we all know, this decade is expected to be the decade of electrical vehicles. The Indian EV market still is in its infancy. The primary technology driver for this e-mobility system is power electronics. Building blocks for EVs are batteries, traction motors, and power electronic converters. Technologies for these building blocks must improve to provide vehicle range, safety, reliability, life, and flawless operation. So few sessions of this FDP are designed so as to address these issues and enlighten the participants with the latest technologies. At the outset, I welcome all the participants, especially I thank the speaker of today's sessions, Mr. Dr. Deepak Reddy Garu, who have accepted our invitation to deliver his address for the inaugural session. Thank you, sir. Thank you very much. And finally, I congratulate Team EEE for drawing 67 participants from 18 different states across the country. And speakers from various countries also have accepted our invitation to deliver this session or to share their expertise with the participants in the area of grid integration as well as electric vehicles. I thank one and all for accepting our invitation and joining these sessions, and hope the participants will have a fruitful session for the next 5 days. Thank you one and all.
Thank you, ma'am, for addressing the participants with the insights of the program. Now it's time to introduce the speaker of the day. and it's not only it also inspires the participants to work in this area by introducing the speaker to the audience. I mean the delegates and the participants. I request my colleague Mrs. K. Swapna ma'am to introduce the speaker of the day.
Good evening, sir. Good evening, one and all. Dr. Deepak Reddy Pulagarab received his MTech degree in Power System Engineering from the National Institute of Technology, Warangal in 2014 and PhD degree from the Indian Institute of Technology, Delhi in 2018. He worked as a faculty research fellow and assistant professor of research with the Department of Electrical Engineering in the University of Texas Arlington in the USA in 2018 and 19. During this period, he worked on high performance optimization and cybersecurity of distributed control in microgrids, funded by the Office of Naval Research, ONR, USA. Later, he worked as an assistant professor in Department of Electrical Engineering, National Institute of Technology, Warangal in India for 2.5 years. He is currently working as an assistant professor with the Department of Electrical Engineering, Indian Institute of Technology, Kharagpur in India. Dr. Deepak sir received APJ Abdul Kalam Memorial International Travel Award for IFAC World Congress meeting in 2017 and POSOCO Power System Award in 2018 for the best thesis. Sir has published 11 journals that includes IEEE and IET journals, 16 international and national conferences. Sir has authored a book chapter and has 2 patents to his credit. He is currently has 2 ongoing projects, DST sponsored SRJ project with a worth of 32 lakhs and National Supercomputing Mission DST sponsored project worth of 45.6 lakhs. Including all these, so many students, number of students, faculty and research scholars are gain knowledge from the sir's YouTube video lecture sessions. So thank you so much, sir. We welcome you. And I'm very glad to introduce such a wonderful speaker on this day, on this session. Thank you so much, ma'am, for giving this opportunity. Now I'm inviting Dr. Deepak Reddy, sir, to take over the session.
Yeah, thank you very much, and good evening, everyone. And I really thank the Institute of Technology for inviting me. So especially head of the department, Dr. A. Sujana Garu, and Mohan, who is consistently in touch with me. So yeah, so thank you very much. Let me share my screen. I hope my screen is visible.
Yes, sir. Yes, sir.
Okay. Yeah, before I start this session, I want to ask you a few questions. Especially, I want to ask what are the participants are like? Are there research scholars, faculty, students, undergrad students?
Faculty, research scholars, and PG students, sir.
Yes,
Okay,
sir.
PG students. Okay, then that's fine. So if it is UG students, I should restrict myself to the limited topic. So if it is PG, I can go in deep. So we'll try to not focus on the contents. We'll try to focus on understanding here. So we'll keep it interactive. This is what I fundamentally believe. Interaction makes more better way of understanding things. So we'll keep it interactive. I'll try to pose some questions in between. If you can ask me questions, that's well and good. If not, I'll try to ask you some questions. If you answer, that's fine. If you don't answer, I'll answer the questions. So that's not a problem. So, but only to have interaction, because interaction makes you alert, because this is a virtual session. So obviously we don't have that amount of focus as in a physical sessions, isn't it? So that's why I'm trying to keep it in interactive way. So don't mind if I pose so many questions. Yeah, please take it in positive way. Okay, so there is a small correction in the topic. I thought of discussing the DC microgrid in the first, but later on, now I made to change, because as of I've seen the speakers, they are mostly focusing on AC and renewable systems. So I will try to focus on AC microgrid itself. If you want some details, I'll put some details of DC microgrid, or I can share some slides of DC microgrids with you. Okay? But we'll try to focus on AC. We'll try to see a generic way of designing the controls. How do we design a control? So yeah, a generic way of designing controls, we'll see. And then if you follow this generic design strategy, you can apply to any system. It can be a PV, or it can be a wind systems, or it can be a fuel cell, or it can be a battery. Anything you choose, you directly put this control, it will work. It will perfectly work. So that is why I want to introduce in a generic way. And then later on a specific understanding, we'll go for a distributed control also, and second stage. Okay. So I think most of you already know what is microgrids. So as the name itself indicates, so we generally have a power grid, national grid, isn't it? So here microgrid, when we say, we discuss about the grid which is located in a very restricted or a small geographical area, and where it is supplying power to a limited systems, okay, limited load. So this microgrid has all different kinds of sources like distributed energy sources, diesel generator, energy storage systems, and other components. Okay. In general, you can say simply, if you ask me what is microgrid, it is a simple small grid, which is in a very small, minute in nature. When I say minute, it means it deals with only megawatts of power, not in gigawatts. Okay. So that's why we say it as a microgrid. And one crucial difference, what it comes is, the microgrid is always restricted to a small geographical area. It is not spread over entire the nation. Like, let's say, if someone asks me, like, there is a renewable PV at Surat, Gujarat, and there is a one PV or wind farm at West Bengal, and there is another wind farm at Tamil Nadu. Combining these three, can I say a microgrid? The answer is no. We can only say it as microgrid only if they are restricted to a small geographical area. Let's say in Warangal, if it is spread in only an area of Warangal, or in a small town of Warangal, then we say it as microgrid. Okay, so that's the main crucial difference. Now, what we call then, so there will be certain systems, right, where we have a PV at one point, wind at one point, and some fuel cells or diesel generators at other points of a nation. Then what do we call these kind of systems? So these kind of systems are called virtual power plants. So there is a small difference between virtual power plants and the microgrid. So microgrids are restricted to a smaller geographical area, whereas virtual power plants are not restricted to a geographical area, but it is spread over the nation. Okay. Then, so that's a small difference. As we know, microgrids can be operated in both grid-controlled and island. So can anyone say what is the difference between grid-controlled and island mode? So I just want to see how much you know about these systems before. So that's why I'm asking.
Island mode is nothing but independent operation, sir, and it is a local operation, local supply of power.
Wonderful. So islanding operation is something where it tries to fulfill the local loads without connecting to the grid. So then we should think of, when we arise this kind of situations, we can arise this kind of situations under two conditions. One is grid failure. Another one is deliberate disconnection for the grid because of some try to operate it. So if you see, we already have multiple microgrids in our nation, if you believe it or not, but those microgrids are already operating in islanded mode. They don't operate in grid control mode, but they operate in islanded mode. For example, if you see any apartments or any townships, then what happens? You have a local diesel generator station, isn't it? Whenever there is a power outage happens, immediately what happens? The service person of the apartment will try to turn on the diesel generator and supply the electricity for a few hours, isn't it? They can't be extended to days, but it is for few times, for few hours or few minutes, they can consider providing the electricity, isn't it? I think many of you already seen this kind of scenarios in our India. So the main reason for development of microgrid is to improve the resiliency or reliability of power supply. So there are multiple blackouts happen in US, in Europe, in India, long back from since 19th century to till 2012, we have seen multiple scenarios, and even recent scenarios also we have seen multiple blackouts. So the main issue has happened is, like, under the grid failure or under the blackout, are we should reside in a blackout condition, or can we supply some electricity locally? So that is what the burning question that was raised, and then the concept of microgrid arose, saying that we can do that. But do you know that this concept of microgrid is not started now, but it is started during the time of Edison and Nikola Tesla. Can anyone justify why I'm saying this? So the concept of microgrid.
initially power was supplied by using DC source, sir.
True.
By
So
Edison
initially,
company.
yeah, exactly, Vijay. So initially what happened is the microgrid, the supply which is there, the generation was local, the load was local. We are not transmitting our supply to a longer distance, unlike now what we're doing it. So then what they did is they operated in a local area only, with a limited power. So that is what the definition of microgrid, isn't it? So that is what fulfilled during the Thomas Alva Edison time. And later, after the invention of transformers and high power, like high voltage transmission lines, then the concept as microgrid has perished, and the people have moved to the high voltage grids, isn't it? But however, again we are coming back to our older systems. Why? Because to improve more resiliency. Because we know that there can be any fault happen, there can be any blackouts can happen in the system because the network is spread wide area. There is a possibility that any unforeseen activity may happen. So under such scenario, we should try to improve our reliability, right? So that's why we are trying to, in simply, what we are doing is we are trying to make a friendship between Nikola Tesla and Thomas Alva Edison here. Okay. So why I'm saying friendship is because there are always rivalry between both of them. Thomas Alva, there's a book called War of Currents. If you read it, or if you see the documentary also, you'll know that the rivalry between Nikola Tesla and Thomas Alva Edison. So now we are trying to friend with them. We are trying to build a friendship, the concept between them. Okay. So the islanded operation here, grid connected operation here, can be happen because of two reasons. One, technical reasons. Other one, some economical reasons. So both can be happen. Both operations can be happen smoothly if we design our control properly. Now, main intention in a grid connected mode. What will be the intention of grid connected mode? Let's say a microgrid which has a solar, wind, or some battery storage systems. What does it do? If it has any excess of generation, it will try to give that excess generation to the grid. Okay. How it gives, what is the rule for it? It will decide that all things can be decided based on the market or economics. Okay. Or sometimes technical factors also. But generally, we can supply the excess amount of generation which we have in a local microgrid to the main grid. Few times, there is a conditions where microgrids, what does it do? Although they have excess generation, they doesn't give to the grid. Why? Because grid is not ready to accept that amount of power. So it will try to dump some local loads or some unwanted loads and try to use that additional supply generation. But however, few times forcefully, the grid will ask to microgrid to keep some reserve. It will ask to keep some reserve, such that whenever I need it, you try to provide that reserve for me. So for example, main grid is there, main grid frequency has been good at 50 Hertz. Now suddenly, because of some load change or suddenly some load increase, what happened is the frequency is steeply falling below 49.2 or 49.7, something like that. Okay, it is falling very steeply. Under that scenario, if microgrid has some auxiliary power, I'm not talking about one microgrid, but if you have hundreds of microgrids or thousands of microgrids, which has some auxiliary power, and grid asks that auxiliary power to provide by the microgrids, if they are all starts providing that additional generation or additional reserve which is kept, then that will help grid to improve the frequency. So those kind of response is called ancillary service. Those kind of service is called ancillary service. So microgrids are also expected to provide sometimes ancillary services. The charge for ancillary service is not same as the charge for main supply, normal supply. Let's say if I buy electricity, I buy it 6 rupees per unit, isn't it? But if the generator or if a source is acting as an ancillary service, then it won't sell the supply for 6 rupees. Rather, it will sell at 600 or 6,000 rupees. Why? Because it is holding that reserve. It is generating the power, but it is not supplying to the grid. It is holding it. It is wasting the energy, wasting the money, isn't it? So to capture to get back the complete economics which has been involved, it should charge more, right? Because whenever it is giving, it will take for a higher charges. So that is why the ancillary charges will be different, and it will be mostly it will be higher than the normal supply charges. Whereas in islanded mode operation, So islanded mode operation is not a very feasible solution if you don't have any storage. Storage is mostly mandatory. If you don't have storage, then many challenges will come into the picture. So assuming that we most of the microgrids having its storage, then we can have a temporary power transfer between the sources and the storage. And sometimes we can try to have a balance out with the local loads by shutting down the loads, or by creating some dump loads. Okay, that's how we can have an islanded operation here. Okay, so these are all theoretical aspects. I'm not trying to focus on this, because the main content will be there after 5 to 6 slides. So as a microgrid operator, what do you expect? Can anyone say, as a microgrid operator, what do you expect? Let's say, so in future, it is expected to have a individual microgrids, and each microgrid has been run by private entity. Like I'm being a Deepak, I can start a company and I can run this company as a microgrid operator, right? I can gain some profits and losses there. So, but as a grid or as a system operator, what do you expect from a control?
Continuity of supply.
Wonderful. One is continuity supply. Next.
We can act as a prosumer, sir. We can act as a consumer as well as a producer of electricity, and we can supply for grid.
So we can act in response to demand response. Yeah. But I'm asking in terms of control. I'm asking in terms of control. What you are saying is in very generic way. That's absolutely correct. But from a control perspective, because we are going towards the designing of controllers, right?
Quality of supply.
Yeah, improved quality. Wonderful. Yeah. So, so first of all, I expect my voltage and current, whichever I'm supplying from a grid or from a source, individual source, should be controllable. Do I expect it or not? I should control my local voltage and local current from each source. So this is main condition, isn't it? Then
Yes.
Power balance between the sources and the load. Because whenever you say quality of power supply, continuity of power supply, this all will be possible when we maintain the power balance. If you don't maintain the power balance, frequency or voltage may dip, and that decreases the quality of power supply, isn't it? So, as one of the participants said, quality power supply can be maintained by using proper power balance. Next, economics. Every technology is related to economics. If it is not an economical solution, then it is not a solution, isn't it? Maybe it may be a solution, but that may not be applicable solution. So everything breaks down to economics, whether we should see whether it is economical way of operating it or not. So we should have an economic dispatch. So now the question comes. So all we have is renewables, then where the concept of economic comes. Can anyone say? We are all talking about renewables, PV, wind. So what is the component called economic dispatch? Because we already installed certain amount of sources, so PV or wind. So how can we change the dispatch? We can always run it MPPT.
Maybe the operational cost.
Wonderful. Operational cost is involved, but not from renewables. Renewables also have some involved with the cost, maybe maintenance cost and other costs. But the main factor is storage. As I said, microgrids need a requirement of storage or certain amount of dispatchable sources. Maybe a dispatchable source of diesel generator can be there, because how sure that you will rely completely on renewables? It is not, at least for now, at least for next 10 years, I totally don't rely on renewables, because there is a high uncertainty in the systems. Maybe in future we have a very updated technology and everything, it may be possible to rely on the renewables. But as of now, at least for next 10 to 15 years, I don't rely on the renewables completely. So I should use some backup sources, maybe battery systems. You know, lithium ion battery cost, how costly it is and how scarce it is. And in short, if we continue to use these lithium ion batteries, we will definitely go see the perishment of lithium, which is usually found in very few places of the earth. So especially Brazil and some other countries, South American countries. So that gets perished Obviously, we don't have we can't completely depend on that. That involves cost. And some sources, like some people say, why don't we use fuel cell or biogas type biogas? Biogas is a kind of renewable, isn't it? But however, to generate the biogas, there is a cost involved. It is a cost involved process. So their economics comes into the picture. Although it doesn't come in true nature of renewables, but the subsidiary components or the other components which are there, like batteries, maybe biogas-based micro turbines, or hydrogen-based fuel cells, or diesel generator itself. Because if we are not ready to go for 100% renewables as of now, we can take our help of some amount of diesel generator also. So these are involved with the cost. So we should reduce the cost involved in it. And lastly, a seamless transition between grid controlled and islanded mode. So grid, unpredictable. Anything can happen because it's such a huge wide network. Anything can happen. It can come, it can disconnect, or it can be connected. But as a microgrid operator, I should be ready whether to connect with the grid or not, and that too without disturbing any local loads. I should not disturb the quality of the power supply. I should not disturb the supply itself and to the local loads. And also I should ensure that I should smoothly connect to the grid. So these are the 4 desirable qualities which we expect. Okay. Are we able to fulfill it? Yes, most of the conditions we can fulfill it with the small changes in the control strategies. But apart from this, we have additional requirements also, like improved harmonic conditions. Okay, it is in the improving the power quality, it is in the harmonics and voltage and balance, and improving the frequency response, and many other additional components can also be there. These are like what I categorize as a important one, at least important for now. Now, what are the challenges? If we see all these things, like power to happen a power balance, to control individual source, and to have economic dispatch, what we need is, we need a huge control strategy. Like a high-speed control we need, high-speed communication we need, isn't it? Because to maintain the power balance, we should know at what point what other loads are there, and all the sources information also should be known. So it means we need a high-speed communication. And all these things can be done using certain component called hierarchical control structure. Hierarchical control structure. So anyone heard about this hierarchical control?
Yes, sir.
Yeah. So if someone has already heard it, I'll try to brief it very short here. So hierarchical control, it's nothing but this hierarchy is observed anywhere in India or anywhere in the world. Maybe in an organization or maybe a private organization, government organization, you will find this kind of hierarchy where you have a local people will be there. Let's say, simple example, I'll say our college, because we are all from an academic background. I'll take an example of college. So we have teachers, we have other departments, we have deans and vice chancellors, and we have directors or principals, isn't it? So teachers are local, maybe a device control kind of stuff. We can assume here, where their purpose is to teach student, isn't it? The purpose is to teach student. Whereas primary control is like a HODs. What their purpose is? Their purpose is to, well, teachers are teaching to the students, they should not be overburdened with additional activities, isn't it? Or all teachers have been shared proportionally, or all teachers are shared economically, isn't it? If the teacher is paid high, he will be given with more load. So because to justify his payment, isn't it? Then secondary control is like maybe deans or vice chancellors. What they do is they try to smoothen the discomforts that have been raised because of some actions which have been taken at the head of the department level, isn't it? And lastly, tertiary control is like principals. What their main aim is to have a contract between multiple companies, or contracts between multiple colleges, or contract with parents, so that they can get the economy into the institute, isn't it? The same thing we can apply here also. So device control, the main role is to control local voltage and current. It doesn't intend to do anything else, rather only to control local voltage and current. How? Based on the references provided by the primary control. So as a primary control, as a role of HOD, what they do, they try to share the load, total load in the network proportionally or equally among all the sources available. Whereas secondary control, because of the primary control, if there is any disturbance happen, or if there is any deviations of frequency and voltages happen, or if it is want to do some synchronization with any other microgrid or other grid, that will be taken care of at the secondary control level. And tertiary control, as we all said, as we already discussed, it's about economic operation and type power control. Okay, type power control means if there are two microgrids and in between are two microgrids or microgrid and grid, if there is a tie, like if there is an economic bond has been written saying that this amount of power should be supplied at every time. So that amount of power should be maintained. So who will take care of that action? That action will be taken care by tertiary dispatch control. Okay, this is how hierarchical control is designed. So this type of control is already there in our conventional systems. If you see, we have this kind of control already. We have this AGC control, isn't it? Load frequency control, AGC control, and we have this economic load dispatch, optimal power flow, isn't it? Which is happened at the load centers, which usually happens at the load centers. State load dispatch centers or national load dispatch centers or regional load dispatch centers, they do this kind of task. Whereas device controllers are controllers which are at the generating stations. We already have this in a main grid, but we should adapt it for a microgrid also. But the problem with this is this entire control strategy has been it's been centralized. What do you mean by centralized? Means the hierarchy will be always there from a upward to downward. We can't have a communication between downward to upward. Device control doesn't communicate with primary control. So we don't have that kind of operation here. It is always centralized and it will come in a one flow direction. Uni flow direction. Okay. That's the problem with the conventional system. Any doubts still here in hierarchical control or the concept which we discussed?
Sir, how load requirement will be satisfied, sir, if it is in a uniflow direction from top to down?
Yes.
How this load balance will be maintained, because the local requirement has to be satisfied or designed, all this put together should reach the top level.
Yes,
how this distribution of load or how this dispatch of load will be happening?
Yeah, I got it. It's a wonderful question. I think we all heard about the concept called droop control, isn't it? In a synchronous, yes. I'll try to explain the synchronous machine and how we do it in inverters also. We'll see it. We'll say in a very quick way. In synchronous machine, what happens? Suddenly, if you have an increase in the load, electric load, what happens? Frequency falls.
Frequency drops.
Yeah. Based on the drop in frequency, the droop control, what does it do? It gives a feedback. It goes to a feedback, adds to a prime mover, isn't it? Some component. Yes. That component will try to balance out the thing. It will be adding the primary.
So that means it will be met locally?
Yeah, it will be met locally. Primary control can be met locally.
Okay. Okay. Thank you, sir. Thank you.
Coming to the point, primary control. Yeah, as ma'am rightly posed a question, I'm going to discuss this. There are in inverters. There are multiple ways to implement this primary control. One is as proper centralized approach. Other one is master slave strategy based approach. And last one is, this is what non-droop based. So there is one component called droop control approach, another component called non-droop control. So based on the requirements, usefulness and other categories, people differentiate with these things. So in the non-droop based, what happens is, if there is a centralized control, it tries to get the load information every instant. It using the communication channel, try to get the load information, takes the complete load information, divides by the number of VJs, and gives that information. When we divide it by the number of VJs, what we get, let's say, total load in the network is 10 kilowatt, which has been read by the centralized controller through communication. And there are 5 DGs are there. 10 kilowatt divided by 5 DGs, what do we get? We get 2 kilowatt. Each DG should supply 2 kilowatt. Now, this is valid. This is completely valid if all the 5 DGs are same rating, having the same rating. Let's say one DG is having 10 kilowatt, or another DG is having 5 kilowatt. Let's say 3 DGs are having 5 kilowatt and 2 DGs are having 10 kilowatt. Is it really valid if I share 2 kilowatt by all the sources? Is it correct or wrong? What do you say? Let's say simply saying, let's say in a family there are five children are there. One child 8 years of age, other child 6 years of age, and other 3 children are 4 years of age. Is it right to expect them to all to bear the same amount of load or bear the same amount of weight while doing the same task? Is it valid?
No, sir.
No, right? So that is what the concept here is. I'm trying to explain. What 2 DGs having 10 kilowatt means it has a 10 kilowatt of capacity, and why do we load it only 2 kilowatt? I will load it more because the margin of capacity is more there. So what do? I got total 10 kilowatt load divided by 5 DGs. What I got 2 kilowatt. Now, with this 2 kilowatt, I will try to multiply with the ratio of generation. What is this ratio of generation? Ratio of generation is nothing but individual DG rating divided by total DG rating. So for my example, I took 2 DGs with 10 kilowatt and 3 DGs with 5 kilowatt. Total rating will be 25 kilowatt. Sorry, 35 kilowatt. Total rating will be 35 kilowatt. Now, what do? Total load 10 kilowatt multiplied with, let's say DG1 is having 10 kilowatt rating, multiplied with 10 kilowatt divided by 35. This is what I'll do. What do? I'll take the total load multiplied with DG rating divided by the total DG ratings. So this gives me a proportional value. This doesn't give an equal value, but rather this gives me a proportional value, which I can allot. So that task is taken care by centralized controller. So did all of you follow this statement, what I said?
It's followed, sir.
Yeah. Actually, I don't have an interactive pen. I did not get my interactive pen here.
No.
Yeah.
No, it's understood. Well understood.
Yeah. Okay, thank you. So then comes to master-slave strategy. So here it is very simple. What happens is, in a master-slave strategy, let's go with the same example as a children example. So there is one person who is of 15 years of age, and there are other persons who are of 5 years, 6 years, and 7 years of age. So what does he do? The 15 years of age person, he knows that he can't carry that weight for a longer distance, but at least he can initially put that weight on him. So what does he do? He takes a 20 kg of bag on his shoulder instantly when it has been given. He takes a 20 kilowatt bag, and he now shares this 20 kilowatt proportionally among all other siblings. Let's say there are 4 siblings are there who are of age 8, 6, 5. So he will proportionally share that weight which he has taken, total weight which he has taken. He will share it proportionally among these. So what is the difference here? It is in the centralized control. What happened is the one remotely located centralized control will take care of everything, and there is no need of any high capacity sources here. But in master-slave strategy, what happened is I needed a big capacity generator. Like in the previous example, I took the children of age of 8, 6, 4, and 3, isn't it? But here, when I'm talking about master-slave strategy, I took a 15 years age of children. Okay, child. Why did I take? Because I assumed that he has a good amount of capacity. So that is how the master-slave strategy works. Like one DG will be there with a high capacity. He takes any change in load, he takes on him, and then he distributes among all the sources available. Okay, so the main source which is taking the load will act as a master, and whereas other sources will act as a slaves. So this is a master-slave strategy. Modified master-slave strategy is something like, say, in the master-slave strategy, what happens is one DG gets overloaded. One DG gets overloaded, isn't it? At least for a short time, it is getting overloaded. In modified master-slave strategy, what happens is we don't depend on only one master. Rather, we take multiple masters and which are randomly picked, based on their available capacity. Wonderful. You should understand this component called available capacity. It means if the DG capacity is 30 kilowatt, but we are only loading around 2 kilowatt, the available capacity is 28 kilowatt. So based on this available capacity, we randomly select masters. Here we don't need high capacity DGs here. We don't need that big capacity DG here, one big DG which is there in master slave, but we can modify that here. Okay, we use a modified master slave strategy here. But all these are communication based. They are all communication driven. If you don't know the load information, you can't do the sharing of load. That is for sure, that you should understand here. Okay. So in a centralized control, the communication is from all the points, from all the load points to a centralized control point. Whereas in master slave strategy, you don't need a load information, but you need the master information should be shared to all the DJs. So master will automatically take the, see, simply example, master is like grid. When you turn on the light, light will be automatically turned on, right? When you switch on the light, light will be automatically turned on, isn't it? It will glow immediately. How does it happening? Somehow it is supplying the power. And we all know current flows through the limited resistance path, and it sees a closed path here, and immediately current flows through it. So that happens in a master slave strategy. The DG will try to see the limited resistance path. From a control perspective, it sees a limited resistance path, and it tries to supply that amount of energy needed for the load immediately at that moment. So any change in load now doesn't need any communication here, but master himself knows that change in load. And once he knows the change in load, he distributes the information. And he provides the information to the slave through a communication. I hope you understood, right, what I'm trying to say here. Anyone facing difficulty in understanding this?
No, sir.
Okay, thank you. Yeah, please feel as comfortable as possible. Just treat me as some colleague or some teacher, not a problem. And ask as many questions as possible, okay? I don't feel bad if you ask me questions. And I really appreciate that rather. Okay, these are all what we discussed in non-group based methods. Mostly they are communication based. As we already discussed, they are somehow directly, indirectly, they have involved with communication. But in a group control, we don't need any communication. How does that work? I'll just give an example here. So example goes like this. Let's say VSC1, VSC2, VSC3 are there. VSCs are like voltage source converters, which are usually used for generators, isn't it? Okay. Just give me a second. Yeah. Just give me a second. I'll try to change this thing. Slides. Okay. So I directly jumped into primary control. I should have discussed a small information about this device level controls, because this is what important is. Okay, designing of device level controls. First, we'll focus here. I think you all can see the slides, right?
Yes, sir.
So, yeah. We'll see what exactly here it is there. In the left side, I think where my cursor is there, that is a DC source. How do you have the DC source? How do we get the DC source? That is a secondary part. Maybe you have a PV with battery where you can have a regulated DC voltage. It is possible. Or somehow you have fuel cells or some kind of sources which can maintain this DC voltage. Somehow this is DC voltage is maintained from sources. That is what I'm saying. I'm not worried about this voltage fluctuation here. I'm assuming that this is fairly an ideal DC voltage. Even if there is a smaller voltage fluctuations, it can be manageable. That's an assumption which we made. Now, since we are talking about an autonomous microgrid, we're talking about autonomous microgrid, not a grid control system. What we should do is we should regulate our voltage and frequency at the terminal point. Why? Since we are talking about autonomous mode, do we have any source which can regulate our voltage? Yes. We don't, right? We usually, our own sources, local sources should maintain it because there is no other one who is maintaining voltage. If there is a grid will try to maintain the voltage and frequency. But here we don't have grid, autonomous operation, islanding operation. So voltage and frequency should be maintained by these sources. So here, so when I say design of device level controls for VSA dispatchable sources, why I consider dispatchable source? Where dispatchable source I assume this because I assuming that this DC voltage is maintained by some sources. So PV is not expected to maintain this DC voltage because if I have only PV, I expect it to operate in MPPT. So if it is operating in MPPT, maintaining a DC voltage is really difficult there. But if I have a PV with battery, I can do that. Okay, PV with battery can be a dispatchable source, or fuel cell can be dispatchable source, or micro turbines can be dispatchable source. Okay, which can regulate this DC voltage. Now, this DC voltage is connected to the voltage source inverter here, and that is connected to LCL combination here. I'm talking about electrical components here. What is this LCL does? This first RF and LF, which is there, it acts as a filter. What does it filter out? It filters out the current harmonics. It filters out the current harmonics. Whereas CF, it filters out the voltage harmonics. Overall, what do you expect to get as an output here is a filtered voltage and filtered current. Okay. So simply, if I fire this voltage source inverter with PWM, using some sine PWM or SV PWM, any PWM technique, what do I get? I get pulsed waveform here. Voltage will be pulsed here, but however, the current flowing through LR will be a bit of sinusoidal. I don't say purely sinusoidal, a bit of sinusoidal in nature. Whereas across C, you will get more of a sinusoidal voltage and more of a sinusoidal current. That is what the main role of here. Is it clear? So this, if you see here, the red marks, that is an output which has been looked at this point, VI-ABC. At VI-ABC point, you will see this kind of pulses. Now, the main aim of this device level control is to regulate this voltage and also frequency at this point. How do I achieve this? So, can anyone say, how can I achieve this?
By providing
feedback control.
Feedback control.
Wonderful. By providing the feedback control, we do it. So we are trying to apply our control theory, which we discussed, which we learned in our control systems. Okay, we'll try to apply that. Is it fair enough to directly take a voltage V0 information and pass it to a PA controller? Can I do that directly?
Yeah, we can do it.
Okay. Now the question is, if you said we can do it, isn't it the V0 is a sinusoidal waveform?
Yeah, but
can I apply a PI controller, proportional integral control, for continuously varying signal?
Like it is.
Because sine is a continuous, right? Continuous waveform.
Yeah. Whereas sine is in a continuous waveform, you can apply PI control over here.
Not exactly. Although if you try to apply it, your response will not be smoother. You won't get a pure sinusoidal waveform or something. You won't have a controllability here. You will lose a controllability. What happens is, so what we do is we don't directly give the ABC, like sinusoidal waveform, the PI controller. Rather, we should do a transformation here. That is called synchronous transformation, what we call it is, or which we use it here. What does it do? We try to transform a sinusoidally rotating or sinusoidally moving signal to a stationary signal. How can we do it? If a signal is sinusoidally moving, I should change it to a stationary signal by using a Clark's and Parkes transformation.
Yes.
So how many of you are comfortable with this Parkes and Clark's transformation? Okay, I feel most of you are not comfortable. I'll try to cue it in a, I'll try to use one code and I'll explain you. Is it okay for you?
Yes, sir.
Say, don't worry about the content. As I said, I'll initially don't worry about the content. If I could able to establish full detail, you only worry about the things which you have learned. Did you learn it perfect or not? Okay. Even if it's short, please don't scold me later. Okay. Just give me a second. I'm trying to open that. So in the meanwhile, I'll ask you a question. I think most of us from a science background, all of you know that the theory of relativity.
Yeah.
Yeah. What does it mean? If let's say a bus is moving at 10 kilometers per hour and you are moving at 5 kilometers per hour. So what is the from theory of relativity? What is the speed? What is the bus speed with respect to you? Bus is moving in 10 kilometers per hour, same direction. If I don't worry that I did not mention direction. Same direction. Bus is moving at 5 kilometers per hour, or 10 kilometers per hour, and you moving at 5 kilometers per hour in same direction.
Means like it will attract the.
No, a relative motion. What is the relative motion between you and the bus?
Opposite.
5 kilometers.
5 kilometers per hour, isn't it? So, aren't we reduced 5 kilometers distance here?
Yes.
Now, if a signal is moving sinusoidal means with time it is varying, isn't it? If somehow I change the reference, if I somehow I change the reference with respect to the time at the same speed how the signal is moving, then how do I see the signal?
Stationary.
Stationary. Wonderful. So that is why we say ABC to DQ as rotationary frame. Rotationary reference frame. It means the reference which we have. So in for sinusoidal waveform, the reference which we consider is constant reference. Whereas in DQ transformation is also called rotatory reference frame. Why? Because the reference frame itself is rotational. It's been moving with the same speed of signal such that it gives me a constant information. Are you able to understand what I'm trying to say here?
Yes, sir. Got it.
Yeah. So I'll just show it in a figure also. Yeah, maybe you will understand that more better way. Yeah. So this is a small figure, small program, which I usually use it to students to explain things. Yeah, if I run this code, here you have a blue line, you have a yellow line, and you have a red line. R, Y, P, R phase, Y phase, B phase. R phase and Y phase and B phase are varying with respect to time. Are you able to see that, the variation? If not, I'll enlarge it. Are you able to see that variation? Increasing, R increasing, B reducing, yes, isn't it? The resultant line of this RYP is black one. We know that. How do we calculate resultant? If you do remember, in rotating magnetic field, resultant magnetic field, 3/2 times of sum of all those things. Resultant in synchronous machines, you might have heard about this. Rotating magnetic field magnitude, resultant magnitude. Anyone aware of that?
Yes, sir.
A rotating magnetic field magnitude. How do we calculate? The same way we can calculate the resultant of this RYB phase. At any given point of time, your resultant is like this. But since R and Y and B are changing with respect to magnitude, with respect to time, the magnitude changes, the resultant will rotate at synchronous speed. That is why rotating magnetic field will come into the picture, isn't it? Are you able to understand what I'm trying to say?
Yes, sir.
The same way, what happened to the D and Q? If I design my reference frame, D and Q are reference frames here. If I design my reference frame, which is rotating at the same speed of resultant magnitude, what happens? Then this resultant magnitude, which is there, the black one with respect to green and purple, isn't it constant?
Yes, sir, it's constant.
So that is what the D and Q components of your ABC. When you do the ABC to D transformation, this is what you get. And what do you see? D component is a projection around the D axis and Q component is projection around the Q axis. The resultant vector projection on D axis and Q axis. That is called your resultant vector D component and resultant vector Q component. It means whenever you do that ABC to DQ transformation, you're trying to get that equivalent resultant value and you're trying to project on D axis and Q axis, which is rotating on a synchronous speed. This is what simply ABC to DQ transformation is all about. So here we are trying to apply the general theory of relativity. That's all. Isn't it interesting?
Yes, sir.
Is it clear, all of you?
Yes, sir. Yes.
Yes, sir.
We'll stop here. Yeah. I have this multiple codes for ABC to DQ, ABC to alpha beta. I made on my own. Actually, I designed it for my students, especially undergrad and postgrad students. So to visualize things. Okay. So let's go to our lecture again. So this is what we do. ABC to DQ transformation about. We transform a rotating signal, which is continuously varying with respect to time, in a sine form. We'll try to rotate in the same direction because sine is nothing but, if you see in a space domain, it is circle. In time domain, it is sine. But in space domain, it's circle. We have seen that earlier also. I think you already seen the resultant vector also there. So I'll try to rotate my synchronous frame, D and Q axis reference frame, in synchronized with the resultant vector. Thereby, I get D projection and Q projection. Okay, that is fair enough. D and Q. Then what is this zero? Zero is something like redundant component, but yet it is important component. Why? Zero is why we introduce zero means. So people are confused. Sir, I can do it from ABC to DQ. I can do it. But once I got DQ signal, and if I want to see it in ABC, how do I do it? I can't do a transformation there, right? To have a fair enough component transformation, to get this invertibility, this matrix to be invert, I can inverse that. So what the clerks who has designed that, clerks and clerks who have designed it, they added this zero component, taking from symmetrical component analysis. I think power systems, all of you know the symmetrical component analysis. Zero component is nothing but zero.
Yes, sir.
So that is what it has been taken here, and it has been used. And this has been used because it will be help us in easy transformation from ABC to DQ and DQ to ABC. Okay. So that is what we do it here. So once we do it, what we get is signals as constant signals. We get a constant signal. Sinusoidal signal has been transformed to constant signal. Now I can apply PI controller. Isn't it? It is straightforward to apply PI controller for constant.
Sir.
But there is a challenge here again. No, there is no challenge. It is straightforward. But how do you design your PI controllers? When I said designing, how do you tune KP, KI values? Randomly, hit and trial. Generally, what I used to do during my undergrad is I hit and trial. Later on, after knowledge, I improved myself. I understood the math regarding this, and then I changed to other structure. I'll put on that here. Control this voltage. what should I control? What is the immediate factor that I can control? See, let's say if I apply KCL at this point, the current that flowing through the capacitor will control the voltage. Do you all agree on it? The current that flows through the capacitor. And you all know that the current that flowing through the capacitor is nothing but the current that coming towards the capacitor and the current that leaving away from the capacitor, isn't it? I minus I naught. This I naught is purely based on load. Load will decide it. I don't know. I have no control on it, isn't it? Network load. Whereas this I, can I control this I? To control this current across this capacitor, can I control this I? Yes, I can control this I. So by controlling this current, I'll try to control this voltage. That is why I have this inner current control and outer voltage control. Outer voltage will control the voltage and inner current control will control the current. Now the question raises, why do I need to control the current? Can't I directly control this VIABC, this input voltage VIABC to control voltage? Answer is yes, I can do that. So instead of assuming that I get inner current control, or instead of assuming that this I reference, I can assume this PI controller which is there for voltage control will directly generate me a signal, this VIABC, signal VIABC. I can assume that. But you should all know that these voltage source inverters are current sensitive device. By any chance, if the current flowing through the inverter increases beyond its rating, this inverter switch gets damaged. And inverter switches are too costly at a higher rating. So we are not affordable, or we don't risk our voltage source inverters by abruptly designing it. But somehow, if I put this in between, the output IDQ reference is obtained from this voltage controller. If I can restrict this IDQ reference, let's say this voltage source inverter is having a rating of 35 amps, and I put a limit, I put a saturation point here, upper saturation, lower saturation, saying 35 amps. What do I get advantage? The reference that goes to the current controller is maximum of 35 amps. It doesn't go beyond that, isn't it? The reference that goes to this current controller will maximum of 35 amps plus or minus. It doesn't go beyond that. Thereby, it will forcefully restrict this current flowing through. Although the control doesn't may happen. I'm okay if the control doesn't happen. But I should protect my switch all the time. Even if it doesn't meet my control requirement, I'm okay with it. But I should always safeguard my voltage source inverter. So when this gets saturated, this voltage reference tracking may not happen. But definitely, the current flowing through this converter will be restricted. Are you able to understand what I'm trying to say here?
Yes, sir.
Yeah. So coming to this designing aspect, so we all understood this concept of ABC to DQ transformation of a signal. But how do we transform this ABC to DQ to the network? Network also to be transformed, right? If I want to design a controller for this, I should know the plant model first. I should know the plant model, only then I can design a controller. To design the plant model, because signal is in DQ, plant should also be in DQ. So that transformation can be done here. Like if you see here, if I transform this dynamic equation which is there, I minus I naught. This is what the equation I explained earlier also, consider it taken. And if I put this V naught signal, I naught signal as this V over DQ, E power J, epsilon T. What does the epsilon T indicates? Because D and Q rotating at synchronous speed, this epsilon T indicates that omega T. Okay. Epsilon of T indicates omega T. Omega is synchronous speed in radians per second. If I put these values in this equation, if I differentiate it, this is what I get. Because omega is also with changes with respect to time. Omega with frequency is also changing with respect to time. So differentiation will be by-part differentiation. It is not single differentiation, but by-part differentiation. So in DQ domain, you get an additional component, this component. You get an additional component that is called cross-coupled component. That is what we call this cross-coupled. Why do we say cross-coupled means? In D equation, we get Q component, and in Q equation, we get D component. This is cross-coupled components which we have there. Mathematically or analytically, if you observe that, we get these components. So when we design these controllers, we should take care of these cross-coupled components also. Okay. So simply by taking care of the cross-coupling components, this is how the voltage control and current control look like. You have additional components here, these cross-coupled components and other components. How do we do it is simply writing the dynamic equation for the, because plant we are considering. So first we'll design this current controller, this system. First we design this complete system, L, RL, RF and LF and current control. This system we'll consider, and we'll design the PI controller for current controller first. For that, we have this equation. What this equation is called? This is dynamic equation for the LF and RF in D component. D component. This is dynamic equation. In this, because of the cross-coupling component, which we discussed in the axis DQ components, we get this IQ component and ID component. We know that. And if you see here, VID and VIQ are nothing but here the voltage V component and Q component. That component is mostly having a relation like this. This is anyone who has studied the basics of inverters, they know this. This is a basic relation. You can assume that this is approximately, the VID is approximately equal to VDC by 2 into MD. MD is nothing but modulation index of the PWM. D-axis modulation index of PWM and Q-axis modulation of PWM. So we get VID and VIQ in terms of VDC, that is DC voltage by 2 into MD terms. Here, the MD MQ, what should be the MD MQ is UD is a control signal that is coming from a current controller. This current control output is UD. This current control output is UK, D-axis and Q-axis component. And if you see here, there is omega naught LFIQ and VOD. Omega naught LFIQ and VOD. There are two components which are there. Somehow I should eliminate that, and I should get only UD there. I should get this entire component should be eliminated. This entire component should be eliminated and get only UD. How do I get it? If I eliminate this VOD, how do I do it? Since it is minus here, I should add here. And since this is plus here, I should minus here. If I do this, and if I put here, directly what do I get is this. I'm eliminating all internal components, which is additional components. Thereby, I can easily model my entire plant like this, where GC of S is again a PI controller, which we should design it. Okay, this comes down as a simple first order system. And designing a PI controller for first order system is very straightforward. By using a pole zero cancellation approach, we can do it. What do I do? Because PI controller has a pole at origin and a zero at KPKI values. Okay, the zero value will be decided based on KPKI values. So the zero of this PI controller should cancel out the pole of the plant. So if I take KP and KI values in such a way that the zero of this PI controller will cancel out with LF S plus RF, that is pole of this, then I can say that PI controller is designed. So KPC is equal to LF by tau C, KIC is equal to RF by tau C, where tau C is nothing but some constant. You can take any constant there. But when I said you can take any constant, there is again a question mark there. That is, can I take 10 to the power of like 4 value or 10 to the power of 5 value? The answer is no. You want your controller to be faster enough. You should have a faster control. But any fastness is valid? Answer is again no. Faster enough, but slower than your switching frequency, because PWM has some switching, isn't it? So your PWM switching frequency, you should your PI controller, the current controller should be slower than your switching frequency. Maybe 5 times or 10 times or slower than the switching frequency, but faster enough. So why I took here 5 to 10 times? Can anyone say? 5 to 10 times of switching frequency. Can anyone have a wild guess? In any plant, settling time, how do you define settling time? In a system, how do you define settling time? Four to 5 times time constant of the plant time constant, isn't it? Do you all agree on that? 4 to 5 times of plant time constant?
Yes, sir. Yes.
So anything beyond the settling time, it means the dynamics of the switching dynamics has been already settled down. So since already switching dynamics has been settled down, if I create any new dynamics, that is also can be easily accepted by the systems. That's why I am taking 5 to 10 times slower than the switching frequency. Are you able to understand my point here?
Yes.
Yeah. So that is how we design our current controller. Okay. Then comes to voltage controller. In a voltage controller also, we'll take the dynamic equation. So so this here ID, IQ are the control parameters. So it's the same way we should compensate. We should eliminate this cross-coupling component and external output IoT components. So that you can, by selecting this ID star as this, you can do it. When we do that, you will only have a UVD component here. Now, if you see here, this entire system can be reduced by eliminating the cross-coupling and other components. It can be reduced it can be reduced like this. We have CF, that is capacitor dynamics. This is 1 by tau CS plus 1. How do I get this? I got because I eliminated this 0 of this PI controller, and this has been got eliminated, and the closed loop transfer function will be 1 by tau CS plus 1. If I properly design PI controller like this, I get the transfer function as that transfer function like this. So that transfer function has been put here, and voltage controller is there. Now here, it is not that straightforward. Reason being, it is second order system. It is not first order system. Rather, it is third order system rather, because here also I have one more pole. So it is a third order system. And since it is a third order system, it is not straightforward method. There is a approach called symmetrical optimum approach. The technique which we use it here is called symmetrical optimum approach, where you see this here. We should know that one point here, phase margin is always associated with the damping. Do you all agree that? Phase margin, in a Bode plot, phase margin indicates the damping. Positive phase margin, positive damping. Negative phase margin, negative damping, unstable system. So in a system, when I'm designing a controller, what should I expect? I expect phase margin should be positive. And over to that, I expect that phase margin should not change, at least for a smaller changes in frequency or smaller change in values, should not change. So here, if you see this Bode plot, open loop Bode plot of the system, any point if you take, the phase margin will change drastically, even for a small change in frequency or small change in the system parameters. But at this peak point, by the change in frequency, the change in phase margin will be more or less 0, isn't it? At this peak point, the phase angle, variation of phase angle with respect to frequency is almost 0 at this point. Peak point, we have that component, isn't it? So considering this condition, I can calculate the peak value, frequency associated with the peak value. Once I get the peak value associated with the frequency associated with the peak value of the phase, now I select phase margin. I will put any random phase margin between 30 degrees to 70 degrees, positive value. Using that same omega m and this 30 degrees and 40 degrees, I can calculate the KPV and KIV values. I'll share the slides. You can go through it. I'm not, because we are running short of the time. I'm trying to fasten this. We can get this KPV and KIV values. That's how we design our controller here. Do you want me to continue on this topic, or do you want me to show the simulation of that? What do you prefer? I'll don't take more than 5 to 10 minutes. Do you want me to give detailing on that, or do you want me to show the simulation of that?
Sir, simulation, sir.
Yeah, okay. I'll open the simulation just a second. Yeah, sorry, it's taking more than usual time. Yeah, in meanwhile, if you have any doubts, please feel free to ask. Yeah, this is a simple system which I have shown in the block diagram also. I took ideal DC source, inverter, then L, RL filter, C, and RL, and some load, some random load. Okay. Here I have a voltage control and current controller. If you see, it will be exactly the same way which I shown in the block diagram. See, it's the same voltage control, exactly the same way. And this is a current control. This is also exactly the same way. And if I show you how do I calculate the PI controller, I use the same formulas which I have shown there. So this is the formulas I have usually written right here. VOD ref is a reference value of the voltage which I want to control. Frequency is a reference value of omega naught is the frequency of the reference. VDC, LF, RF. LF, RF are actually tuned for this system. We already calculated it using the amount of harmonics it is expected to eliminate and all those things. We have calculated this. LF, CF, LC, RC. LC, RC are randomly chosen, but LF, CF, and RF are properly calculated one. Switching frequency, based on the switching frequency only, we will calculate LF and CF, which is coming around 10, switching frequency is around 10 kilohertz, what we do. Okay. And TS is the sampling time, simulation sampling time. Okay, that is not a bigger factor we should consider now. So if you see here, TC, I have taken 10 divided by 2 pi FSW. As I said, which I can take it from 5 to 10 times. So I took 10 times. So KPC, KIC value I calculate directly. And as I said, phase margin, I can select anything between 30 to 70 degrees. So I took in between 50 degrees. And I calculated the KPV and KIV directly here. I calculated the KPV and KIV directly here. Using the same formulas which we have. Now, the same form, all the form, I used everything as a formulas only. I did not use any random here. And if I run this, you will see the properly controlled system. So I'm trying to control it VOD ref, that comes from 310 value. Just let it run. So within no time, let's say I'll just run it at 1 point. Seconds. Yeah.
Sir, there are two controllers here, one voltage as well as current controllers.
True.
When you place two controllers, will there be any lag in the system operation, sir?
No, actually, it purely depends on how speed you are designing it. I am designing my controller. See, my switching frequency is 10 kilohertz, ma'am. So
okay.
Let's say 10 kilohertz. So 1 by 10 is 3 into 2 pi. This is my switching frequency time constant. This multiplied with 10 times I'm taking. This is my response time of a current controller. And over to this, again, I'm taking it into 10 times. It means 100 times. If I design my voltage controller also 10 times slower than the current controller, 100 times. This is my response time. In the worst scenario, this is my response time.
Okay.
It is less than 1 millisecond.
Less than 1 millisecond.
Near to 1 millisecond. See, you can see that also. How quickly it responded. So here it is not controlled, but next signal it is controlled. See? Here it is controlled. Or if you want, I'll change the value in between and also I'll show you. So let me take a step. So 0.3. 3 volt DSF. Value VOD ref. Let's some 10 volts or 20 volts. Let's say 50 volts, bigger value, not problem. say, I'll just do this. So response time will be in a milliseconds. And this can also be directly applied to hardware system also. It's not like it was only restricted to simulations and mathematics, everything is restricted to simulations. Even if you do it for hardware, you will find the same response. Maybe you might be finding some more noise in that, but see, you can see, ma'am, by the next cycle, it has been responded.
Yes, yes.
So it doesn't take more than a millisecond. So that is how we can design. So it's very straightforward and simple. I hope all of you understood here. I think I already exceeded 3 minutes of my time.
No issues, sir. Topic is very interesting. You are dragging our attention like anything.
So yeah, any doubts, participants? If you have any doubts, please feel free to ask here.
Sir, excuse me, sir.
Yes.
What is the range of this controller gain, sir? KP, KI, KD in this? In general?
I can't say what exactly the values will be, but yeah, for current control, KI value comes around thousands. Sometimes it may lead to hundreds also, 600, 700 also it can be. So it purely depends on your LF, RF, and CF values: capacitor value, inductor value, and resistor value, and also switching frequency. So for my case, I'll show you my case, then you can visualize. It is not stiff, this thing. KPC, KIC. See, KIC is current controller time constant 628. KPC is voltage control time constant. Current controller not time constant. KPC is proportional gain. KIC is integral gain.
Any cap is there, sir, for this?
Any
cap like this, upper cutoff, like lower cutoff, something like that?
No, nothing like that. It purely depends on LF and RF again. Yeah, as I said, upper cutoff. So the time constant of your PI controller should be slower than your switching frequency. 5 to 10 times slower than the switching frequency. So
can it be in lakhs, sir? Is it any possibility like that?
No, lakhs is impossible unless you are using a per unit values, then it can go.
Okay, thank you.
If you're using absolute values, it doesn't go like
that. Participants can unmute themselves and ask in case of any doubts.
I think they have no doubts. Maybe they did not understand anything, or they understood completely.
No, sir, the session is interesting and it's clear, sir. So maybe.
No, my doubts are cleared. I have cleared my doubts during the session itself. Many of the doubts are cleared during the session, sir.
Thank you, ma'am. That will interest us also, like to explain more
Yes.
information.
Sure. Yes, sir. Yes.
Thank you, sir. Thank you very much for a wonderful presentation and a lot of insights in your presentation, where it's a clear-cut explanation. I request my colleague, Mr. Mohandas, to convey thanks and vote of thanks for this session.
Good evening to everyone. My name is Mohandas, Assistant Professor in EEE Department VJIT. It is my immense pleasure to thank Dr. Deepak Reddy sir for accepting our request and gave a wonderful lecture on distributed control based microgrid in spite of his busy schedule. I thank all the participants for spending their valuable time with us. I sincerely thank our director, Sai Baba Reddy sir, for his inspiring mentorship, and Dr. A. Padmaja Madam, Principal, for her constant encouragement. I take this opportunity to thank our HOD, Dr. Sujana Madam, for her continuous efforts. I thank each and every faculty member for putting their efforts for successful of this program, FDP. Thank you, sir.
Thank you, sir. Thank you, Mohandas sir. We request all the participants to kindly